Okay, this is a video just illustrating the effect of the C versus Q relationship on the low duration curve that might be derived. And here I'm going to use the example of the Cannon River with a location at Welch Village. There's a USGS gauging station located there. And I have data from 2005 to 2013 for this evaluation, continuous flow data. The Excel file for this is on the Moodle site for the course. So as you can see here, there is a sheet that's got the raw data in it, which would be just the raw flow data for the Cannon River at Welch. And the discharge rates that are given here are in cubic feet per second. There's the date, the station number, and the U.S. Geological Survey designation there. And these data have been processed to create a flow duration curve by doing the appropriate sorting of the data, and that's what you see here. The dates are given here in this column C, and D has the flow rates that are arranged from smallest to largest. The rank is given here, the percent exceedance, and so forth. And there really is no sediment data that was used in the analysis here, but basically what I'm trying to do with this spreadsheet is to illustrate the effect of the relationship between TSS, concentration, and flow. Because normally we would have such a relationship developed. You would have graph samples of TSS with the flow, and you would try to correlate those two, and there would be some kind of an increase in TSS concentration with flow rate. But here I've basically synthesized the concentrations by assuming basically a linear relationship between concentration and flow rate. The linear relationship is expressed here in these upper two Excel cells. The first is the slope of the relationship between TS and Q. As I mentioned, it's a linear relationship, so you need to have the slope and the intercept. And of course, the intercept in this case is 0, since the relationship presumably passes through 0. When the Q is 0, the TSS is 0. And so one can select this however they want. You can make the slope larger or smaller. Of course, it's positive. And then to make the relationship uncertain, that is to have some error in it and more realistic, I just superimpose on it a standard deviation. And the spreadsheet calculates some random numbers that then calculate deviations of the concentration off of the relationship between TSS and Q. So to illustrate how this works, if I have the slope of 0.02 milligram per liter per cubic foot per second, if I put a standard deviation of 0 in here, that means that the relationship is perfect. And if I were to go down here to where I plot the concentration versus discharge, you can see that there's a perfect linear relationship between concentration and discharge. And of course, that's rather unrealistic, because you never find that to be the case. Maybe the relationship looks pretty good, but usually it's never the case. So to be able to modify that somewhat and make it more realistic, I'm just putting in here that say that the standard deviation is 10 milligram per liter. And generally a standard deviation would depend on the flow, but here I'm keeping it as a constant. The model then, or the spreadsheet then, calculates some random numbers that are multiplied by the standard deviation to calculate the deviations of the concentrations with respect to the flow, or off of that straight line. So if I insert that and we go down and look at the relationship, you can see there's no longer a perfect straight line, but that you could fit a straight line through this relationship, but you can see there's deviations off that straight line, which actually increase as the flow rate increases. So this is not exactly what you'd normally see, but this is a rather rich data set, because usually you wouldn't even have this many grab samples to work with. All right, so assuming that that's our relationship, first let's look at what the flow duration curve looks like for the Cannon River at Welch, and that's shown here. That was derived by taking and ranking the data and calculating percent exceedance. And then I have a plot here showing the discharges as a function of time for the period of record, and the red dots or red symbols are the sediment concentrations that have been calculated or synthesized here. So you can see the variation in the sediment concentrations and different dates. So we have a sediment concentration calculated or represented for each of the measured flow dates. All right, so then we can take those, we take the standard concentration, which was 25 milligrams per liter. That was listed here. That's the water quality standard that's set for this site. I'm not saying that's actually what the water quality standard is for the Cannon River. I'm just putting that number in. And using the flow duration curve, I can calculate the load duration curve. This is in kilograms per day. And the blue line would be the load duration curve for the water quality standard. And then taking all those samples, which presumably are not real samples, they are synthesized values of concentrations that occur for each of the flow rates that is shown. And of course, as I mentioned already, the concentrations are a function of the discharge, but there's a random component in there that then leads to this cloud of points that you can see, which are not falling on a solid line. You have some spread here. If I were to have zero standard deviation, we'll just go up here and do this again, just to show if I make this zero standard deviation so that the relationship between concentration and discharge is perfect, then I get a nice solid line. There is, for that case, there is no variability around the relationship between concentration and discharge. But now if I go back and put 10 in here for the standard deviation, then I get this variability around the line. And it would be the lower envelope of this cloud of points and the upper envelope of the cloud of points, which would represent the range of load duration curve I would want to use to calculate the loads for this site. What's shown here in this little table below here are the calculations of the loads for the different hydrologic flow regimes. The 0.05 would be the high flow regime, 0.25 would be the moist flow regime, 0.5 would be the median, 0.75 would be the dry, and 0.95 would represent the low flow regime. And the numbers that are given here in each of these categories or in each of these columns would be the values of the load taken from the load duration curve. So you can see these different symbols here. I'll call those my box Whisker plots. They're not, there's no box here, but I have a maximum, I have a minimum. I could use 10% for the minimum and 90% for the maximum, but here I use the maximum and the minimum. I have the mean value, you can see by the diamonds, and then the green box here, green square is the median value. I have the 75 percentile, and the 25 percentile also plotted on there. So within each of the flow regimes, I have what I'll call my box whisker plots. Basically, that's what they represent. I just don't have a box around them. They have all the features such as the median, the mean, the quartiles, 25% and 75%. And the whiskers would actually be represented by 10% and 90%. Here I have maximum and minimum, which are even more extreme than using 10% and 90%. But it'd be possible for me to calculate the lower 10% values and the upper 90% values. Okay. Now to actually do the plot, I said that I would try to show this to be able to illustrate how to construct box and whisker plots directly on your own load duration curve. I calculate here in each of the categories as to what the median is, what the first quartile is, the third quartile. The first quartile is 25%, the third quartile is 75%. Then, of course, there's the maximum value and the minimum value. But basically, you can see here what the command is within the data, within this box. The box would be, I'm calculating the median for these values. These are values of load, and those are in column L, and those correspond to the values that are associated with the events that are equaled or exceeded only 10% of the time. So those would be the values that are, see, here's 20%, 10% would be right here and a half. So it'd be all the points that you see in here would be the ones that were that are being taken to calculate the mean, and all the values for all the different flow regimes are given in column L and summarized here. Okay, so see that here. So there's some commands that are done here to do these calculations. These make it simple or easier for you to be able to quantify, not for you necessarily, but make it easier for the analyst to be able to do these calculations. So somebody could take this command, let's say you could take this spreadsheet and apply it. You can copy your own flow duration curve in here and just use this for doing your analysis. The only difference would be is that instead of having these thousands of data points that I've got for load, you'd have the finite number of data points that you have available from the grab samples that were in the data set that I gave you for the Little Cannon River. All right, so here we have the calculated from the values that are in column L. We have the calculated values of the median, first quartile, third quartile, and so forth. And so then if I wanted to, I can calculate by going across each of these rows that this number that's in this column here for the median, that represents a load that occurs 10% of the time. This value here corresponds to a load which occurs 30% of the time. This one occurs 20% of the time. This one's 30%, and that's 10%. If you add up all those percentages, they should all add up to 100%. The load then is calculated by multiplying the first number by 0.1, the second number by 0.3, the third number by 0.2, the fourth number by 0.3, and the fifth number by 0.1. Adding those together, I get 61,761 kilograms per day. That would be the median load. First quartile is 40,000, third quartile is 92,000. The maximum value is really high, 433,000. The minimum is really low, it's 19,000. And the mean should look somewhat like the median. It's 97,000. Okay, so that's a simple way to introduce box and whisker plots into your diagram. One thing that could be done if you want to actually put boxes on there, basically you just have to go up here and ask to put in a shape. And so if I do that, put a box in there, I would draw a box and make it hollow. Let's say, format shape, and make it so that it's no fill. It has a solid line. I can adjust how thick the line is, and this can be adjusted in size. If I do it without messing up my graph, it'd be nice. And I could move this over so that it lines up with the upper part of the box should be the 75 percentile. The lower part of the box should be the 25 percentile. And so I could do that for each of these five fairly easily. It is done manually. It'd be nice if it was done more automatically, but that's one way in which you can put your box whisker plots together. And of course, I can put a solid line across the middle. I already for the median where the green line is, where the green box is right now, or the green square. I have that as a square. I could make that a green line, and that green line would then pass. If you adjust the length of that line, because you can specify how long the line should be, you make it so it goes all the way across. That would be your median. And that would be the typical thing you'd see with box whisker plots. If you wanted to, then you could make a straight line going up and down on top. Those would be the whiskers that you see for the box. For the assignment, I don't really care whether you put those boxes on there. Mainly, I would like to be able to see you have the upper and lower limits that you see here with the median, the quartiles, maximum, minimum, so forth, and the mean.